In this section we're going to talk about Erlang as a functional programming language and also talk about the other functional programming languages that are around and how Erlang compares with those. Okay, let's get started. We assume that you understand Java or C or some procedural or object-oriented language. We're now talking about Erlang, and we've said the basis of Erlang is functional, and what that means at the simplest is that the Erlang system works like a calculator. What a calculator does, you remember, is if you type in an arithmetical expression like 3 plus 2 times 4, what you get out is the answer, which is, in this case, would be 11. So Erlang works by calculating a value which is the result of evaluating an expression. Now, it's a bit more complicated than that because we've added concurrency, fault tolerance and so on, but the basis is this model of calculation of results of expressions. We have that model, but it's more complicated in two ways. First of all, we don't just have a built-in set of operators like plus and times, we can define functions for ourselves. And secondly, it's more complicated because there are different sorts of data. We can have complex data like lists or tuples. We can also have functions as data, and indeed combinations of those different things. So we've got this model of calculation, as in a calculator, but we have more complex data, more complex operations. Now, why is Erlang functional at basis? Well, the model is simple. We just have values. We don't have things like references, pointers, and so on. We just have values, expressions whose values are calculated. The functional model also supports some high-level patterns that have become very important in practice, things like MapReduce, because it's a simple value-based approach to programming. Functions themselves can be values, and those can be embodied in, can be passed as arguments to or results of high-level operations like map or reduce. And finally, we don't have side effects. We don't compute by changing the state of a machine, so our data becomes immutable, and that makes algorithms clearer. But immutability also means that we can do things in a much cleaner way. If we have immutable objects in an OO language, then these objects become like values in a functional language. And that means that if we're computing with threads which share any state, we can do things like caching values and sharing values entirely safely. And we never get into a situation where we have an inconsistency between what we see in one thread and what we see in another. So immutability buys an awful lot of safety in an OO or an imperative language. So immutability is a good thing in itself, and we see that by design we have immutability in a functional language. Okay, Erlang is pragmatic. I think you've probably realised that from the discussion we had last time about it coming out of the desire in Ericsson to build a language that did the things that they wanted. We've said Erlang is functional, but it does allow some side effects. So, for example, the way that communication is handled in Erlang is as a side effect of evaluation. Now, we're not going to go into that in detail in this mini MOOC, but if you follow up the MOOC by looking at Erlang concurrency, you'll see how that works. But Erlang does avoid some sorts of side effects. It doesn't have a state which can be updated by assignment. So it has what's called static single assignment, and we'll find out more about that later on. So it's a pragmatic balance between having no side effects at all and having the sorts of side effects that you see in Java or C. It's pragmatic in another sense. It has types, but it has a more freewheeling approach to types than Java and C, for example. And we'll find out a bit more about how it compares with other functional languages in a minute. Now, it has a more freewheeling approach in the language, but there are tools that one can use, like Dialyzer and Typer, to check type correctness, to check that certain sorts of type errors aren't happening. So though it's the language itself is relatively freewheeling, there are tools that one can put on top of it that will help to ensure the safety of the programs that we write. So there's that nice pragmatic balance. Now, if we look at the functional programming language landscape, there are quite a lot of languages that are called functional out there. A lot of languages are what are called strongly typed. They have rich type languages. What we mean by strongly typed is that any type errors you get in the language, you will get at compile time. You don't get runtime type errors. Now, we have languages like Haskell and Miranda, which have what's called lazy evaluation. What that means is that evaluation of expressions is driven by demand. So instead of the traditional evaluation, which is it's called strict evaluation, where arguments to functions are evaluated as they are passed to the function, so before the function body is evaluated, in Haskell and Miranda, arguments are only evaluated when evaluating the body requires that. So it's quite possible an argument doesn't get evaluated at all, or it's possible that a composite, a data structure, is only evaluated partially. And this allows for all sorts of complex infinite data structures in the case of Haskell and Miranda. Now, there's another difference between these two families of languages, and that is that Haskell and Miranda are entirely pure. They don't have any side effects at all. And that is because side effects and lazy evaluation fit very badly together. Laziness forces you to be pure. That's because you don't know when particular parts of an expression are going to be evaluated, so you don't know when that side effect, if it was there, would happen. On the other hand, languages like ML and OCaml and F# have strict evaluation, and they do have some impurities. Different languages have different balances of impurity, just as Erlang has side effects, has impurity in its communication primitives. So a different class of languages from Erlang, strongly typed rather than weakly typed, and within that class, Haskell and Miranda have lazy evaluation, the others, ML, OCaml and so on, the ML family, are strict. But these languages are strongly typed, as I said. All type errors happen at compile time, if they happen at all. At the other end of the spectrum, there are weakly typed languages from the Lisp family. And these are inherently non-typed, if you like, because they have built at the heart of them, they have an eval function. So you can construct data and then evaluate that data. So there's no way that you know in advance what type the data you construct will have when they are evaluated. But Lisp has a long history. Lisp was first invented over 50 years ago, and descendants of Lisp like Common Lisp and Scheme and Racket are in widespread use today. But at the heart of those languages is sophisticated use of macros and use of eval to make the languages very strongly reflective. So again, that differs from the sorts of things we're doing in Erlang. Now, if to be a functional programming language all you need is to have a lambda to allow you to define anonymous functions, then we have a huge class of functional programming languages, because Java, JavaScript, Ruby, C++, nearly every language you can think of is getting a lambda, is allowing the facility of having anonymous functions, simply because they've proved to be so useful in functional programming paradigms like MapReduce and so on. So you can see that's the general functional programming landscape, and you can find on the website references for more information about functional programming in general and some of these other approaches to functional programming. But what we're going to do next is find out a bit about how the MOOC is going to work, and then we'll move on to actually discovering how Erlang works and installing it for ourselves. Okay, so that's it for this session.